Bismillahirrahmanirrahim. Assalamu alaikum. Today we are going to start with the lecture number 23rd, and in this lecture we will implement all the arithmetic instructions that we did in lecture number 22nd. So before going to start the lecture number 23rd and implement all those arithmetic instructions in assembly, we will review what we did in lecture number 22nd. So here you can see in lecture number 22nd we first studied the shift and rotate instructions. We discussed about the logical and arithmetic shift, so shift left and shift right and so on, shift left, shift right and so on. You can see here shift left, shift right, and then shift arithmetic left and arithmetic right. So in shift left and shift right, what happened when we shift any register, either 16-bit, 32-bit or 64-bit register, what happened like so in shift instruction, when we shift any register, either 16, 32-bit and so on, either we shift left, then the most significant bit will move towards the carry and so on. Similarly, for the rotate right and rotate left, same operation happen. However, we can involve carry, so the carry bit was also being used. For example, here is a carry bit, and here is our complete register. If we rotate carry left, then whatever the bit is inside the carry, it will move here, and the most significant bit will move towards the carry and so on. Similarly, the opposite is for the rotate carry right, so the least significant bit will be copied inside the carry bit, so and the carry bit will be moved or shifted toward the most significant bit, and rest of the bits in right shift will move in the right direction, left shift they will move in the left direction and so on. Then we studied about the shift left destination and shift right destination. So in shift left destination we use shift left destination, then we have one register, then we have other register, then we have the amount of shift, how much we want to shift this register. So there were three operands that we were using here. So one register, second register, or one register memory operand, and the amount that we want to shift. Then we discuss about the shift and rotate applications. For example, how we can shift multiple elements of an array. There are 3 or 4 elements. We want to shift all of them either left or right, whatsoever, and we can use them as a 64-bit, 128-bit and so on, consecutive all these elements in as one or as a whole. Then also we use the if in case we want to show all these elements or all these, in case if we want to show the binary values inside the register, whatsoever the values inside the register we want to display its equivalent binary, then what we are doing, either shifting left or right, and then we were monitoring carry, either the carry is set or reset. For that purpose we are using the one string array, and in this string array we were replacing elements either 0 or 1 based on the value of the carry. Then we discuss about the multiplication and division instructions. So there were multiplication instruction, integer multiplication, division, and then I division or signed integer division. So these were the instructions that we have used, we have gone through in lecture number 22nd, and today we are going to implement all of these instructions, and we will see how they behave in assembly language and how we can implement what type of operations we can achieve in assembly language by using all those instructions. So let's enjoy assembly language. So now here we have opened a new project. You can see here the name of this project is lecture 23rd and examples, and in this project we have this skeleton program. We have included all these include files like Windows include, kernel 32, lib and include file. then we have included MASM32 include and left file, and then we have data and code, and then we have the starting section. So now we are going to start with our basic. For example, first we are going to have examples about the shift left and shift right. For now, if we say move EAX comma 2 or whatsoever you can use, then we use if shift left EAX comma amount, how much you want to shift left or you want to shift right, and so on. For example, if I use this 2 is in decimal here, and if I'm using this 2, and if I build this project, just simply build this project. So very simple one. So you can execute this one. We have to see these registers. So we have these registers. Okay, so now you can see all these registers, and now we are going to move EX with 2. So EX will be assigned value 2 here, you can see, and if I shift EX with 1, then definitely it should be 4, because when we shift left, it is just like 1 bit shift left is just like multiplication by 2, and so on. You will see other examples in this during these examples and so on. Here, this is the one of the simplest example. If I want to modify this one, like if I use shift right EX comma 1, then it will again, the value will remain same, the value will be changed. How it will change? I want to just build this project, and you can run this project. So initially the value for this was 2, then I have shifted this 2 at the left side 1 bit, then the value will in EX has been updated, it became 4. If I shift it again, then it will become 2. So this is one of the simplex example. Now for example, if I want to print this one, output byte 32 duplicate comma 0, and so on, and if I want to print the values, for example, if I say invoke double word to ASCII EAX comma address of output. If I say output 1, the name of this one will be output 1, and so on. Now I want to display this value, so I will write invoke stdout comma address of output 1. I want to use another one variable, for example input 1 byte 10 and duplicate whatsoever the duplicate is amount, and if I want to say here that invoke stdin comma address of input 1, and then the amount, the number of keys that we can press. Now we don't need to go in steps, we can directly run this one. So initially, for example, if we want to print the values for EX after shifting, so we just build this one. So here is stdin, just build again. So here is the input 1. Okay, so this one is successful. Now if I want to run directly, so I just run this one. So here the output is 4. This 4 represents that when we print, when we shift this one, it will print the output whatsoever the values inside the registers. If you want to run it in a step-by-step mode, you can see. So this is the output window. Here you can see the output of this one. So output is 4. So if I press enter, the program will terminate. Now after that, if I want to shift like 2 times, it will be like multiple of 4, and if I shift 3 times, multiple of 8, and so on. So I just build again, and if you want to run it, you will see the output is 8 here. So this is the way you can use the shift as a multiplication. Also we will see the examples next one. So this is shift left, and for example, if I want to shift right, this EAX, how many, for example, I have 1, so it's like division by 2. So after this one, I want to print this value. Just you have to build this one. So build is successful. So initially it will print the value. So initially it will print 8, then there is 2, as you can see it is like 82. So before that one, I think it would be better if we print something else for the carriage return. So I just save this one. Here is like output 2, and I just write byte. 13 is for carriage return, line feed, and 0. And I want to print invoke stdout address of the output 2. So if you want to print this one, just compile and execute. So you can see here, so first result is when we shift 2 times at the left. So initially EX has the value of 2, and I have shifted 2 times at the left side, multiply by 4, and then after that I shifted right side 1 times, and it is like division by 2, and so on. So this is about the shifting these values, shifting the value inside the registers. Either you can use 32-bit, 16-bit, and so on, all these registers. After that, shift arithmetic left, shift left, and shift right. Now we are using the rotate. So this is about the shift arithmetic, shift left and shift right. So sorry, this one it should be here is the shift right. Build this one. So initially we have to check it again. I think I just comment this one. So there is one error because we are shifting to 8 is okay. Now the problem is when we are using invoke, then the best way is we have to push these values before going to print. So if I just compile this one, run in a step by step. So initially it is 2, then it became 8. So we are going to shift right, it become 4, and it will ask for input and so on. So there's input, and then it will end the program. Now what is the problem? We are getting the wrong result here, even though there was a shift left here. The problem was the shift invoke, stdout, and all these instructions, they modify the value of EX register. So now to make it correct, what we have to do, so here is shift left 2 times. So first of all, I just run what is the, you will see the difference. There will be some error here. What is the error? I just compile this one and I want to run that one. So here is 8 and 1 again. So this is okay. And if I press enter here, now what I want to do here, for example, if you want to invoke in a step-by-step manner, sometimes you will notice that, so first is move EX is equal to shift left is equal to 8. So when we are going to invoke DW to A, you can see EX has been modified. Actually this DW to A or STD out and all these one, they have the, so invoke STD out, this address output. So now you can see the value of EAX. Now here shift right EAX 1, and now it became 1. Actually it should have been 8. EAX should have been 8, but now all these statements, they have modified the values of this EAX, and now even though the result is, fortunately it is the correct result, but it should not be. You can change these values and you will see what is the result here. For example, if I want to move here 4 maybe 3 for example, and multiply by 4, it should be 12. 12 means C, and okay, so it's good. So you can see here it is 12, we multiply by 4, and then again when we shift right, the result is 1. So this is wrong, it should not be 1, it should be 6 or something. And when we shift right this EAX, the problem is all these 3 instructions that we are executing, they are using the EAX as one of their parameters because we are calling these procedures. So the best way is when we execute these instructions, we push EAX, and before going to perform this one, we have to pop EAX. Now the result should be correct one. The point I wanted to make here is that when we are calling all these procedures, then maybe they are using they are preserving the values of all these registers. Otherwise, if they don't, you have to push all these values. So you can see now the result is correct because initially it should be 12, 4 multiplied by 3, because EAX has the value 3. So here you can see the value of EAX. Here the value of EAX is equal to 3, and when we shift left 2 times, it should be 12 multiplied by 4, and then we push EAX to preserve its value. Then we are performing to print out this value and so on, and after that we just pop EAX. So after popping, we have the same value for EAX like 12 or B in hexadecimal, and when we shift right EAX 1 time, then you will get the value 6. So this is about the shift left and shift right about the EAX. I want to save this one, so it should be example1.asm, example for example 2.asm. So now, so example 2 have been saved here. Now we are going to perform another operation for the shift arithmetic left and shift arithmetic right. So here what will be the difference? If I say minus 3 multiply by 2, and I just pop this one and divide by 2 and so on. So I just save this one, and instead of using shift left, we use the shift arithmetic left SAL and shift arithmetic right. So here you can look at this one, the example. So we have to build this one again. So build is correct. Now if I want to run this one, sorry, it's going to build. So we have made the changes inside the ASM2, so we want to make changes in ASM. We will save this one. So minus 3. So now we are going to use the shift arithmetic left. Here you can see if I say move EAX minus 3, and then we perform shift arithmetic left and then shift arithmetic right. So when we say shift arithmetic left, so it will preserve the sign and then perform the shifting operation. So here if I run this one, so it is minus 12. You can see the output here. It is minus 12 and minus 6 after performing shift arithmetic left and shift arithmetic right. So this is the way you can perform shift left and shift right. Now one thing, I will save this one and we can perform the rotate left and rotate right. So we can say file, save as example3.asm. It has been saved. I just rename this one as a generic one. So now what we are going to do here, we are trying to use the rotate left and rotate right. They are almost similar, but in rotate left and rotate right, they have the privilege to use the carry also. Now here, for example, if I want to use the move EAX comma 12, or maybe for example if I use the 4 and I want to use rotate right EAX comma 1, and here I want to use rotate left EAX comma 1. Save this one. Now one thing, we have to push EX, and before performing this another operation we can pop EX. So this is about rotate left and rotate right. So we just build this one, okay, and we just run. So first one is rotate right. Here you can see we have to rotate right. So if we rotate right 4, it will become 2, because you can see here if we want to rotate this one, so for example 4 was equivalent to 0 0 1 0 0 and so on. If we rotate this one, rotate right, it will be 0 0 0 0, all these zeros, and this one will be moved here and 0. So this will be equivalent to, for example, so there are multiple zeros and so on, and this will be equivalent to 2, and here this will be equivalent to 4, and the same will be performed here. When we rotate left, then previously it was 2. When we pop this one, it will be equivalent to 2, and then when we perform rotate left, so this one will be transferred here, and then it will become 4 and so on. So just see this one. So this one is output 2 and 4. So this is about the rotate left and rotate right. So next one is the I want to save this one. I think I should leave this one as it is, and then we now STC is the set carry, for example. So if you want to see the STC, just debug this one. So here you can see I want to debug this one and see the carry, the flags. So if I want to set the carry, first instruction will set the carry flag. Here you can see the carry flag has been set. Next one is move EAX is equal 4, rotate right. So now this is simple rotate right, so the output will be almost similar here, but I wanted to show you that set carry statement will set the carry flag. Now if I want to use RCR, rotate carry right, for example if I say rotate carry left, in this case what will happen, and here I see I want to use rotate carry right, and you will see, and CLC is, you will see this one. So there are two instructions. I want to copy this instruction here and put it here. Set, save. So first, to see what is the purpose of STC. STC will set carry, CLC will clear the carry. So this is clear that we are using two instructions. One is the STC, second one is the CLC. So here what we are doing here, first we are going to set carry, then we are going to move assign 4 to the EAX. Now we are shifting left along with the carry. So carry flag, whatever the value is, it will be, so for example, if the carry flag is 1, if the carry is equal to 1 and the value for this one is equal like this, so the output will be, the output should be like this one, shifting left and then carry will be added. So if the carry will be added, now you can see this operation. For example, I want to save this one and just successfully build. So first is a set carry, so carry EX is equal to 4. Now rotate carry left, it should be 9. Why it should be 9? So here you can see it was, first we are going to shift this one, left side, so it is 1 bit has been shifted and this one was inside the carry, and now this carry has been transferred to this one, and the left side, at the left side it was 0, so 0 has been transferred to the carry, so it is rotating all these values. So you can see also, if I want to rotate left or right, the value of this carry flag is also changing here, because the rightmost value here, if it is hexadecimal 0, then it should be 4 binary zeros. So one most significant bit of EAX, whatever the value is, when we perform rotate carry left, it will be copied inside the carry flag, and previous value of carry flag will be transferred to the least significant bit of the EAX register. So in this way you can perform rotate carry left and rotate carry right. So for example, if I want to perform another rotate carry left, RCL1, RCL EAX comma 1, so now you can assume what should be the value. So if this is the value that is stored inside the EAX register, now the new value should be, so the new value should be like this one. So this one will be shifted here, all these bits will be shifted here, and carry value should be in this one, the rightmost bit or the least significant bit. So this is the way you can perform this one. If I just compile, so I have just push EX, pop ES, clear carry, rotate right. Okay, so I just build this one and run this one. So it was 9, for example, along with the carry it was 9. So here the value was 9 along with the carry. When I shifted left, then I have multiplied 1 time again, so it became like the 18, because the carry was equivalent to 0, so carry has not been added here. And then what happened for all this 18, when we said clear the carry, whatever the value of carry was, and again we are going to perform rotate right, so it's like division by 2. So this is the liberty to use of this rotate instruction to use the carry flag and so on. Now this was the example where you can see we are using all these rotate, shift, and the rotate arithmetic, and the rotate shift arithmetic, and also shift logical shift, and so on. Now these are the examples. Now we are going to move towards the other statements. I want to save this one. So the same, I just remove this one, and then we will use the shift along with the destination, shift left destination, shift right destination, and so on. So here, for example, if I want to say move EX comma 0 0 0, I want to write 4 hexadecimal. All these are zeros. So move EX on this 0 0, all these zeros. So it is 4. So this is 4 in EAX. Then I want to say move EBX comma 3, and all these 0 and 3 in hexadecimal. So now what is the purpose of using this shift destination left and shift left destination, shift right destination, and so on? So what's our purpose? We want to shift this EAX, for example, 4 bit at the left side, and these 4 bits which will be available here, they will be filled with the values of this EBX register, whatsoever the number of bits we are shifting. And if we use this EBX as a destination register, then its 4 bits will be, most significant 4 bits will be transferred to the EAX. So shift left destination, so shift left destination comma is the EAX comma EBX comma 4. So now what should be the output of this EAX? You can see in this example. So initially the values which is assigned to EAX is 4, EBX is equal 3 0 0 0 0 and 3. Now we are going to shift left destination EX comma EBX comma 4. So this 3 has been transferred, or these 4 bits have been transferred to the least significant 4 bits, because we perform left shift how many times? 4 times. If I want to perform multiple times 1 bit or 2 bits, so these bits will be transferred from the most significant bits of EBX will be transferred to the EAX. So it depends how much amount you are going to shift. If I want to shift more than this one, so to make it like 3 2 1 and so on, so if I want to shift 8 bits, then definitely the input, the 8 bit in the least significant 8 bits of EAX will be assigned, or will be included with the 8 bits of the most significant 8 bits of the EBX. So if you just run this one, so EAX has the value 4, and EBX has the value 3 2 1 0 0 0 and 3 and so on. If I want to shift left destination EAX comma EBX and 8, so you can see these most significant 8 bits of EBX register have been transferred or have been shifted to the least significant 8 bits of this EAX register. So now the new value for EAX is 0 0 0 and 4 3 2 and so on. So on the other hand, what I want to do, if I want to use shift right destination EAX comma EBX comma 4, for example. Now one thing you notice here, the contents of EBX or destination register are still same. there is no effect on the contents of EBX register, so they will always be same. It will not affect their values. So we just save this one, run this one, and here you can see that initially is 4 and 3 and so on. Now one thing you should notice here, it is 4 3 2. Now it was when we were shifting left destination. Now we are going to shift right destination. Now to see the output here, you can see, so the least significant 4 bits of this destination register have been transferred to the most significant 4 bits because we are shifting right. So most significant 4 bits of the EAX register. So least significant 4 bits of EBX register have been transferred to the most significant 4 bits of the EBX register. So if you can see the analogy, for example, I can give you the example here. In the case when we shift left, then EAX will be at this side, and the amount is, for example, amount is 4 bits. If the amount is 4 bits that we want to shift, so what will happen? So EX will be shifted left side, 4 bits will be shifted left side, and EBX will be here, and from this EBX 4 bits, 4 most significant bits will be transferred to the least significant 4 bits of the EX if the amount is 4. So in this is the case when we perform the shift left destination. If it is 8 bits, so 8 bits, but 8 most insignificant bits, so it is 8 bits. Now the same thing will happen if we perform, so how many bits we are going to buy? In this case EBX will be here, for example. So least significant 4 bits if in the case if the amount is, for example, 4. So least significant 8 bits will be transferred or will be moved from the EBX to the most significant 8 bits or 4 bits of the EX, and so on. So this is one of the simplest example that you can use to shift all this one. So shift left destination, shift right destination, and so on. This is a very good example because if you want to copy some bits from the register and another register or memory operand and so on, or memory variable or the location, so you can use this type of example or this type of technique to accomplish that one. Now we are going to move towards the, for example, if we need to isolate the bits, for example, so I want to save this one file, save as. So here is our same example, how we can isolate the bits. If we have register, for example, EDX is a register, and if this EDX has some information, for example, EDX has the information like first 7 bits 0 0 1 0 0 1, they show the year, so it should be like 0 0 2 4 6 and 7 bits, they show the year. Then we have 4 bits for the month, 0 0 1 1, these are for the months to show that what is the month. And then we have the date, there are 31 maximum days, so we can use 5 bits more. So these 5 bits will show the, for example, 0 1 0 1 0, so these 5 bits show the date, 4 bits for the month, and these bits show the year. Now for example, if we need these 4 bits, if we want to copy these 4 bits into the if we want to copy these 4 bits, into the EAX, or if we want to transfer them into the EAX, then how we can do that one. So I want to comment this one from here. Now you can see, so we have year, and then this one is for the month, and this one is for the day. So we need these 4 bits. So how we can do that one? For example, if we say move EX, so instead of moving this one, because this is 16-bit information, so if we want to use DX only, here if I want exclusive R DX comma EDX comma EDX to remove the contents, to clear the EDX and EX registers. Now what we are going to do here is move AX comma DX. Now we have copied the contents of AX DX register into AX. Now shift right, we want to shift right AX, how many bits? 5 bits. Now we want to remove all these 5 bits. We want to remove all these 5 bits, and then what we are going to do is AND AD, sorry, this one is the shift, this is AX, and AX we are going to perform 1 2 3 4 all these one, and the how many bits we need only 4 ones here in binary. So this is the we can directly use the hexadecimal. So these are the 4 binary values: 5 6 7 8 9 10 11 12. Okay, so this is we are going to perform, or you can perform the same one by using the hexadecimal values and so on. So we have the AX register. We first shift right AX register, then we preserve these 4 bits, and then we remove all the other bits in the AX register. So in this AX register you will see the value of this month only. If I just so this value is too large, 1 2 3 4. Okay, so here we have to represent the binary, because otherwise it will consider as a decimal value, so value will be too large. So I can, okay, so first clear the contents of EX register, then EDX register. So EDX has been cleared, EX has been cleared. Now we want to move this one, so this is 000266 and A register. So A, this one is 10 in decimal, so it is A. Then we have this 6, then again next 6, and then we have this 2. So 266A in DX. So this is a part of this register EDX, that is called the DX. Now the next operation is we want to copy all these values in EAX. Shift right all these. So we have shifted right 5 times. This is the new value, is 133 in hexadecimal, and we want to remove all these bits. We need only 4 bits. So 3 is the value in the month. So even though if you see here in the month value, this is a 3 value inside the month, and if you want to print years or days or whatsoever inside this any register, even you can use the shift left destination or shift right destination to copy these values from the registers and so on. So this is one of the examples you can see here. I can just save this one. So now we want to apply the technique to shift the elements, multiple elements of an array. So how we can shift the multiple elements of array? First of all, we have to define the array. For example, array is array1, and it's the side. This one is like the element has the value, for example, double word. So double word, and these values are values inside this array. Duplicate of these, for example, 99999 in hexadecimal. So how many nines? 2, 4, 6 and 7 and 8. So these are the 8, and how many times we want to duplicate? For example, if we want to duplicate 3 times, and if I say array size is equal 3, so it will duplicate. So how many times? Array size times duplicate. So we are going to duplicate this array size for multiple times, like array size is equal 3. Now after this one, what we are going to do is we want to perform the shifting. So array has array1, or simply I just write array and don't need to write array1 and so on. So array has the 3 elements. For example, if I write in comment, so array, the first element is all these 999 and so on in hexadecimal, and second element, it has the value array plus 4, array plus 4. So this is array plus 0. So whatsoever the memory location this array keyword represents, array name of this array represent, it will be the same location. Then the next 4 bytes have this same value, and then similarly for the next 4 byte it will be same. So I just copy and paste this one, and this will be it. Now what we want to do is we want to use this one as the higher order byte, higher order double word, middle order, or we can say middle double word, and we want to use as a lower order double word. So if we combine this one, it will be 8 and this will be 12 bytes total. So it will be 12 byte total. In total it will be 12 bytes. So we want to shift all these 12 bytes either left or right, whatsoever you can perform. So this complete will be shifted. How we can perform this shift? First of all, we need the area or the move. First we need the index. So ESI is equal, for example, 0, and then what we need to do is we need the shift right. We want to shift right, so we want to start shift right from here. We will shift right this one, then whatsoever the value of carry is, we want to add this carry here, and along with this carry we want to perform shift right, then here, and so on. So shift right array ESI plus 0. So ESI plus 0 comma, how many times? 1 time. So first of all, we were starting with the higher order byte, then so next one is we do not want to use only shift right, because if you use shift right, then the problem will be that it will not consider the carry. So what we can do, rotate carry right, because carry will be considered and carry will be added in the most significant bit. So the next, these will be added with the most significant bit will be replaced with the carry, and so on, and then the same for the the last element or the lower order byte if you want to use this one. So this is the higher order byte. We are starting with the higher order byte, then we will use this one, the middle order, and then the lower order byte. Just imagine what will be, or just try to guess what will be the output. So for example, if I want to print the output, is so I want to print the output. First of all, what I have to do is move EAX, comma, array. We can directly use this array 8, then invoke DW to hex, because I want to print the value in hexadecimal, so DW to hex, and then EAX is the value which I want to convert into the hexadecimal to the double word that I want to convert, and then address is the output. If I say output, so it will be output 1, for example, or output whatsoever. So I want to print invoke DW, invoke std out, comma, address of output. Okay, so same will happen for the middle order and then the lower order 8 bits or 4 bits of this array. So if I say 4, if I say nothing, so only just error, it's okay. So I can just write it, save it, and here if I want to say invoke std in address of the input is byte 10. So just this is the not the efficient way to stop the program. Right now we can use that one, then we will see the other methods, input 10 and so on. So I just build this one, so build is successful, and I want to just run this program. So here you can see what is the output. Output is 4, C, 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 and so on. So the last one up to this one is the C. Now why we have got this C, C output and so on? Because initially this is the higher order byte, so I want to just show here. So 9, mostly 9, they will be represented like 1001, then next 9 will be 1001 and so on, and all these bits. So when I just rotate, shift them right, it will be 0, 1, 0, 0. So this is the first byte or the most significant byte, and then the next one will be 1, 1, 0, 0, and then next will be 1, 1, 0, 0, and so on, and this will continue. So this should be 4, this should be 4, because it will start from here, then continue up to here, and then continue from here and so on. But here when we are at this point, the last one should be 1, 1, 0, 0, and this one will be transferred to the, so carry will have this value, carry will be equivalent to 1. So it should be like this one. So this should be the output, like 4, C, 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 and all these C and so on. So in this way you can see, if we print out all this whole complete 12 bits of this array, you will see that how we can achieve this one. So in this way we can shift all the elements inside the array. We can shift them left, shift them right. So this is the right shift example. Now if you want to make it left shift, so if I want to save this one, 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 so if I want to save And if I just save this, I want to save is this, for example, .asm. So I want to make it a right shift example. Now if we want to perform right shift, then be careful, because so right shift means we are shifting from this side and it will continue from here and so on. So in this case, this operation will be reverse. You can make it completely reverse. How we can make it reverse? So I can just remove this one. So it should be 0 will be shifted without carry. Sorry, we will perform shift left, and now we are going to perform, previously we performed shift right, now we are going to perform shift left. So if we shift left, then just be careful that you have to start from here, shift left, ESI 0, then we have 4, then we have 8, and so on. So what will happen if we perform shift left this one, then carry will be updated with the value 1, because this is 9. If this one is equal to 9, then here as we know that 9 is like 1 0 0 1 0 0 and 1. So this bit must be transferred to the carry. So this bit will be transferred to the carry, and rest will be like this one. So this will be like this bit has been transferred to carry, and rest will be, and so on. And the last bit, so the last byte of this one should be, it should be 0 0 and 1 0. Okay, so just let's see. So first we perform shift left, then we will not use shift left again, we will use rotate carry right. So rotate carry left, and then we will use rotate carry. So we will use rotate carry left, so because we have to consider the carry also. So it will be like this one, and now you will see the output, because here the output should be like this one. We just run this program. So you can see first one is only 2, because it should be 2. The first, here you can see, so the first one should be 2, and the rest bits in hexadecimal, they will be 3 3 3 and so on, and even up to the last one. The last one should be only 3. The last one should be only 3, because in the last byte, if it is like 1 0 0 1, then this one will be cancelled here, moved to the carry, and the previous one from the previous byte will be moved to this. So here you can see the output and the example that you can perform shift left, shift right to shift all the elements of the array and so on. Now till this point everything is okay, so we can perform shift left and we can perform shift right to all the elements. So I just want to save this one. So this one is okay. So now this is the one of the application. Now what we want to do, the next application is we want to print the number in binary. Whatsoever the number is in EX, that will be printed in binary. So I want to remove everything here. So we have nothing. So output should be like if EAX, for example, EAX has the value 7, then it should be printed all these 0 zeros, and then 1 1 1. So this should be the output that should be printed on the screen. So we want to convert the values of EAX, whatsoever the value of EAX is, that should be. So we have 32 bits, for example, 32 bits in the binary bits or binary digits inside EAX, and their value is, for example, we don't know the value right now, and they will be terminated by the 0, and this value here should be the we will use this value as a string. So now what we have to do is, first we have to use the save this one. Now we want to move EAX with value, for example, 7. Now we have to start with the logic, like for example, if we say how many times we want to, so ECX will be used as a counter. ECX is equal 32, and we have this loop L1. So this is the counter. This is the counter. This is the loop 1. So here we say, so this loop will continue. So we are starting with the from the 32. We are starting from the 32, and then we will continue towards the 0. So before going to move this one, before going to start the loop, what we have to do, we have to set the offset of this. We have to set the ESI with the offset of the register, of the array, of the name of this array which we have used here is the output. So offset of the output, sorry, so offset of the output. So now what we are going to do, if the carry, we will perform rotate or shift operation. So we have the output here. Now shift left EAX, for example, comma 1. So after performing shift left, we have to jump when not carry. So in case before jump when not carry, we have to move byte pointer, because we want to change the value, pointer ESI comma 0. So at this byte, or at this pointer, or if initially it is, for example, initial starting point, so we are shifting left. So starting with this, the most significant bit, if we first move 0, in case if it is not carry, then we jump to the loop, jump L2, otherwise the same position, it will be replaced with the 1. Now for example, next one is the increase ESI. So here should be L2, here, increase the value of ESI. So ESI is the starting byte of the array, which will be either replaced with the 0 or 1 and so on. So next one should be loop to L2, sorry, L1. So this is the complete. So L1 should be capital here, label is okay. So now what we did here is a very simple logic. Initially we shift left, so the most insignificant bit will be transferred to the carry flag. Initially we transfer enter 0 at this initial bit in the initial byte in ESI in this array, output array, or we can say it ESI. And then in case if we have replaced 0, in case if it is not 0 or not carry, then this logic is correct and we have to move to the L2. Otherwise the same element will be replaced by the 1 in case if it is the carry is set. So this is loop and so on. So what we have to do, we have to invoke the output and then so on. So this is a very simple program. So invoke the output and so on. So it's okay. Save, compile this one. Successful. So here you can see 0 0 0, all these zeros, and in the end you have got 1 1. So this is the output of this program. Or otherwise, if I just change the value, instead of 7, if I use 9, then it should be 1 0 0 1. The last byte or the least significant byte should be 1 0 0 1 in binary. So I just run this one. It should be 1 0 0 and 1 because it is the equivalent of 9 in decimal. So here you can see this is one of the applications. You can use shift left and shift right, or rotate carry left, or rotate left, or rotate right, and so on. So this is another example. Now we are going to move. I will save this one. And then we will perform another example. So this is one of the application. So here, if we want to perform multiplication, for example, if I want to perform multiply by 26, so for example, EAX, move EAX has the value 2. So I want to multiply 2 with the value of 26. So how can I perform this value? So move EX with 2. Then I say, for example, move DX, comma. So initially I just clear the contents, exclusive or EAX, comma EX. And if I say AX is equal to 2, I want to multiply this AX, so move DX, comma AX. I have the value inside this one. I multiply with 4 initially, so multiply by 26, multiply by 26, that is equivalent to multiply by 16. Then so 16, then we multiply by 8, and then we multiply by 2. So this is almost similar. So multiply by 2, multiply by 8, and then multiply by 16. So almost it will be similar. So first what we are going to do, we want to multiply by 16. So multiply by 16 is like shift left dx, comma 4 times, shift left 4 times 2 raised power 4 is equal to 16. And then the next one is we can push this value because we will need this value, and then so push dx, and now again move. So this is only multiply by 16. This area is only multiply with 16. Then we have another one. So now we are not using any multiplication example and so on. So what we are going to do here is multiply by 16. Then the same one is we just copy instead of writing everything. So multiply by 8. This should be multiplied by 8. So So the same 2, so dx will be assigned with 2 and then multiply by 8 is equal to 3, and then so we have multiplied by 3, and now what we have to do after that, we can multiply by 1 also, sorry, multiply by 2 also. So here we just copy this one, this is multiplied by 2, so the result will be multiplied by 2. Whatsoever the result is, this result is already in dx, shift left dx comma 1, this is multiplied by 2, and then now we have to add this result, total result. So previously multiply by 16 is stored inside this one, inside the array or inside the stack. So previous result, that is multiply by 16, is stored inside the stack. Now we have to pop this value, pop ax, and then we have to add the same one, so we have to add ax comma dx. So this is the final value. This one is equivalent to, here the value of dx will be equivalent to dx multiplied by 10. So now we are going to add, so ax is here value, whatsoever the value is multiplied by 16, and then we are going to add both of them. So again the result will be inside ax. So if I want to say invoke dw to add eax, so this is the, just save this one, run this one, so we can run this one, sorry, this is the change, these are the changes which we made. Control copy, and we have to save this one, so we have to run this one. So this is 64, you can see here. If I want to multiply 26 with 3, or 3 is multiplied with 26, so it should be, the output should be, just a minute, I have to compile this one. So if I multiply this 3 with this one, it should be 96. 3 multiplied by, no, this is wrong. So ax is equal to 3, sorry, here it should be move ax. Okay, now there was one mistake here. Actually it should not be 26, it should be 52 instead of 64. It should be 52. The error was here. We have multiplied this one with dx with 16, so we have multiplied with 16, then multiply by 8. Now multiply by 2, here we have to, ax is multiplied by 1. Now what we have to do next is, when we multiply ax with 1, so we have to add before that one, or before performing this one. So we have multiply ax, now we have to add here, add ax comma dx, so it has been added here, and now so this is the complete multiplication. This is multiplied by 2. Now here is the multiply by whatsoever is, and now pop dx, and this should be So this is 52. Now it's okay. The problem was here. You can see here when we multiplied. So first we multiply EAX with 16 and we save this result, and now we are going to multiply the value of means AX. So first we multiply AX with 16 and we save this result inside the stack. Next what we want to do, we want to multiply the same DX with 8. The value of AX whatsoever is 2, so 2 will be multiplied by 8, and then the result is inside DX. The multiplication of 16 is stored inside the stack. Result of this multiplied by 8 is inside DX, and result of multiply by 2 is in AX. So we add AX value and DX value, so we have the multiply by 10. Now again we are going to pop the value of multiply by 16 in DX and add this one. So AX has the value now here at this point is the multiply by 10, and then we add with multiply by 16 and so on. So we have the result output. For example, now if I change the value as 3, so now you will get the correct result. So this is 78, because 3 multiplied by 26 is 78. And now if you want to multiply 2, it should be 52 and so on. So whatsoever you can multiply by 26, you will get this value, the result, by using this one. So this is one of the application. You can use the multiply and so on. So now we are using the other instruction. We will see the other instructions that we have used. So I just comment this one. So for example, we have multiply instruction. You know that in the multiply instruction we use the keyword mult or MUL, and what we are going to do here, I will just give you the review. If multiplicand, so multiplicand is an AL, the value, so I will write here multiplicand is here, then we have the multiplier is here, and then the product is in this one. So if multiplicand is an AL and multiplier is any either register or memory location, and this is 8-bit, then result will be in the AX register. On the other hand, if it is AX register and we have the register or memory location of 16 bits and so on, then the result will be in the DX and AX register. So DX will have the most significant byte, most significant byte and so on, and the AX as the least significant byte. And if it is EAX, is the multiplicand is in the EAX, and we have register or memory location that is either 16, 32-bit or whatsoever, then the result will be in the EDX and EAX both. So for example, if we want to use the exclusive, or I want to use this one, exclusive or EAX comma EAX, move AL comma 12 and multiply. For example, if I want to use the word, for example, you cannot use constant here. If you want to use constant, it will give you error. So the best way is either you define variables or use the registers. DL comma 12 R2. So it is like 3 or 4, whatsoever you can write it here, multiply DL. So you can see the result. I can just compile this one and run in a step-by-step mode. So initially EAX has been 0, AL is equal 3, DL is equal to, here you can see the DL has been modified, so DL is equal to, so I think first we can clear this one. So DL has, so these are two hexadecimal digits that show DL. So DL will be multiplied with the AL, so the result will be inside the AX register. So result will be inside the AX register. However, so this is the, so if we want to use here, so EDX comma EDX and so on. So here you can see, if I just build this one and run step-by-step mode, so for example, so both are 0 0, 3 has been assigned to EAX, mine means AL, 2 is assigned to EDX, and if I multiply, then result is in also AX. So you can assign or you can use any value inside the AL. If I use 60 or whatsoever, you can use the value. For if I use 4, multiply by 2, here initially they will become 0 0 4 multiplied by 2, result is 8, and it has been stored. So 8 is in same in hexadecimal and decimal and so on. So I just save this one and stop this one. If I want to print, for example, invoke DW to ASCII EAX comma address of the output, invoke std out address of the output. So EAX is the value. Right now we have the EAX which has the value. Now I will show you the example where we can use the two registers and combine their value. So just build this one, and okay, I can uncomment this one so we can see the output. Okay, so here you will see the result 8. Now if I want to use the whatsoever the value for this one is 50, so maximum value for DL, you can see if I use 50 here, so 50 by 2 is 100. So unsigned one, for example, if I use the signed one or unsigned one is 50. So 2 raised power 8 is the maximum value that you can use either here or here and so on. Now this is the result, but if I use 150 it's okay. But however, if I use 350, so the problem is AL cannot have the value more than 255 and so on. So just be careful. If you want to use this one, then use AX register. So if you want to use AX register and you want to multiply with DL, it's okay. So in case of AX, what will happen, I just compile this one. Now in this case you will not get any error if I use AX register. So the result here you can see is 188 this should not be the result. The result is wrong. Why it is wrong? Here I just comment this one. So I just save this one and build this one. So initially these registers have been cleared. So 15E is the 350, so we are using AX register, so all these 4 bits, 4 hexadecimal digits. Now 2 is in EDX. When we multiply this one, then what will happen? Then 0BC is inside the so we have the DX. DX is, I think I use BX register here. Because this, it will modify the value of EDX register. So in case of modifying the value of DX register, I want to use the, okay, if I use BX is equal to 22, so here you can see EX is equal to 0, EBX and 16. If I multiply, so you can see one result is in EDX, second result is in EX register result, and this carry flag will be set if the DX register has been modified. In the previous example you have seen. So now you can see here the result. For example, if I use the hexadecimal values, hexadecimal value is 0, 0. So we are using multiplication now. So the DX is 200, and here, so the AX has registered the value 200, and the BX register has 100 in hexadecimal. So now I can just compile this one and run this one. So you can see AX has, sorry, this should be in hexadecimal here to see the example. So AX has the value 200, AX has the value 200. Initially 200 is assigned to AX, so this is complete AX. Now BX has the value 0, 1, 0, 0. If we multiply, you can see the EDX and EBX, their contents have been modified. Actually, we are not concerned with whatsoever the value is inside the EDX is the upper byte, or this one, and also in the EAX. We have the result in only DX and also the AX register. So we have this result. Now how we can combine these two results? So now at this point we have result in these two registers, and these two are 16-bit registers. Now if we want to combine them, there are multiple ways you can combine. The easiest and the most efficient way is what we do: we push AX, and first we push DX, for example. So this one is first we push DX. This is the most significant byte, most significant 16 bits, and then we have push AX, and then next one what we can do here is the pop EX. So EX will be popped and it will have the total 32 bits. So what we are going to do, we are going to push DX inside the register, inside the stack, then we are going to push AX, then we pop EX. 16-bit registers value have been pushed, next 16 have been pushed, and we are going to pop 32. The easiest way. Just compile this one, and we can run this one. You can see. So initially EAX is AX has the value 200 in hexadecimal, 2 and 3 zeros in hexadecimal, and EBX has 0100. These are the hexadecimal values. Now if we multiply these, this is the value 0020 and 0000 in AX register, and this is the BX and DX register. So first what we do, so here carry flag is 1, it means the contents of EDX or DX register have been modified, or there is some addition inside this one. So if I just push DX, then pop AX, or push AX and then pop. So here we have popped these two values, this most significant and the least significant byte. 2 bytes have been popped from the, so this one word EDX and ADX and AX have been popped. So this will be the result. For example, now I just stop this one. If I want to use in 350 and 100, so you can see 350 is more than the AL, so I don't want to use AL, so I've used AX. Then we have BX I'm using. So these are the decimal numbers, and if I want to print the value inside the decimal, so just combine. So now you can see 35,000 is the result. So this is the way you can perform these multiplication and division and so on. And then we have the you can perform integer multiplication. So integer multiplication is almost similar, but the way is you can perform the, for example, so this is okay, so multiplication, then for example this is minus 5, so, and this is 2. If I run this one, there will be the result you can see, but we have to extend this one. So you can see this result is not correct. What we have to do here, first we have to extend this one, minus 5. First I want to use the for AL. Save this one. So first save. So that was example about how we can perform multiplication. Now after that one, what we have to do, we want to perform the integer multiplication. But before going to perform integer multiplication, we have to know about the converting multiple word to double word, means byte to word and so on. So we have to extend them. The examples are like you will see here. So first of all, you can see here, for example, if I want to perform so integer multiplication, as you saw that one in the previous example, here you can see. So this was our previous example. If I use this one, this is our previous. So now you can see here, this is our previous example. Now if I want to use the sign multiplication, for example, minus 5 multiply with the 2, and if I use only this MUL, then it will not give you the correct result. I just compile this one and just run this program. So this is not the accurate result. How we can get the accurate result? If I use I just save this one first, save this one, and if I want to use AL, for example, if I use AL is equal to minus 5 and BL is equal to, and if I multiply with the BL, and I don't need push right now, don't need to combine, don't need anything here, because the result will be saved in AX register. And sorry, okay, so actually this one is here minus, if just check. Okay, so the problem is we cannot print here right now. So if you want to perform the integer multiplication where you want to consider these values, so we have -5 and then we have 2, AL has -5 and BL has 2, and we are going to multiply. So I want to compile this one, and you can see here step by step here. So AL has the value -5, so AL is this 8 bits, and is FB, this is -5 and this 2, and the result will be stored inside the AX register. So FF6, this is the result that has been stored inside the AX register. On the other hand, if you want to use the, for example, AX register is equal to something like minus 2240, for example, and here is the BX register has the value minus 112, and so on. And if I multiply with the BX, so I can just save this one or run. So initially the values are 0 0 0. F0 is the value which has been assigned to AX. Then we have the minus 112 in the EBX, the BX register. If we multiply, so now you can see EDX has been modified. This is the value, because value is inside the DX and the AX register. So DX and AX register, in combination of the DX and AX, they will have the result. So this is negative result or negative value. You can see both of these registers have this value. In this case, you can perform either sign multiplication and sign multiplication or unsigned multiplication. So I can save this one. Now we want to perform, I remove this one. So here now we want to perform division. So for the division, if we do not have only, we have the dividend, and then we have divisor, next one is the quotient and remainder. So in case if the dividend is in AX and here the divisor is the register or memory of 8-bit, then quotient will be in AL register and remainder will be in AH register. In case if we have DX and AX registers, so we have 32-bit dividend, 32-bit dividend, and divisor is register or memory of 16 bits. Then AX will have the quotient and remainder will be inside the DX register. On the other hand, if we have EDX and EX, we have 64-bit dividend and we have register or memory location of 32 bits, then definitely EX will have the quotient and the EDX will have the remainder. For example, we have the value in AX register, it is 40. So we have the BL, we want to divide it with, for example, 10. So if I divide this one as 10, so you can see here we have to use division, div, division, and build this one. So I can run this one right now here. EAX, EBX, they are 0 0. AX is equal to 8, so 40 is here, and 10 is here. 10 is equal to A. If I say div BL, then what will happen? So you can see quotient is 4, remainder definitely is 0, so there is no value inside this BX register here, so it should be 0, so no modification here. There is no modification in the BX because here AH has the remainder, so this is AH, this is AL. So in case if I want to see the remainder, this one is 42 in decimal. So here you will see the remainder. In this case, this AX, AL will have the quotient and remainder will be in AH. If I run this one, so first of all move 42 or to A in hexadecimal, 42 in decimal to AX, then BL has the value. Now you can see AL has the quotient and remainder is inside the AH. So you can take all these bits, like the least significant 1 byte that will represent as a quotient, and the the next 1 byte in EX register, the second least significant byte will represent the remainder, and so on. On the other hand, the other registers, if we perform the 32-bit multiplication division, then AX will have the quotient and remainder will be inside the DX register. So from these registers we can get the results, either what is the value of the quotient and remainder. So this is the introduction about all these instructions that we have studied in our previous lecture. So now we are going to summarize. So in this lecture number 23rd, we have implemented the shift and rotate instructions like logical and arithmetic shift, shift left, shift right, and the arithmetic shift left and right, rotate left and rotate right, and the carry also. If we want to use shift rotate carry left and rotate carry right, and the end in this category we did shift left destination and shift right destination. Then we have seen some applications of these shift and rotate. Then there are some other instructions like multiplication and division. So we have seen the multiplication and the integer multiplication and so on. So these are like few examples that how we can implement or how we can use all these arithmetic and these instructions, rotation and these multiplication division instructions and so on. So this is end of this lecture, and inshallah hope to see you in the next lecture. Till then, Allah Hafiz.